Misión está comenzando. Todos los asistentes están en modo de solo escucha.
Hello everyone, my name is Juan Cruz Curati and I would like to welcome each one of you to our SPR webinar. With the SPR Communication Committee, we are very happy to share with you our first webinar of the year. We are delighted to welcome today's presenters, Dr. Jaime Delgadillo and Dr. Zac Imel, who will be talking with us about machine learning and artificial intelligence and their methodological and ethical considerations for psychotherapy. To briefly introduce today's presenters, Dr. Jaime Delgadillo is a senior lecturer and research director at the Clinical Psychology Unit in the University of Sheffield in the United Kingdom. His clinical interests are in the treatment of depression, anxiety, and addiction problems. He has clinical qualifications in psychoanalysis and in cognitive behavioral therapy. His research focuses on the analysis of routine care data to develop prognostic models and tools to support therapists to personalize psychological interventions in a data-driven way. He has led multi-site clinical trials of feedback and treatment selection technologies in the English National Health Service and is a member of the Expert Advisory Group for the National IAPT program. Dr. Zac Imel is Professor and Director of Clinical Training at the Counseling Psychology PhD program at the University of Utah. Zac is the author or co-author of over 90 scientific articles and book chapters, and is the co-author of the second edition of the book, The Great Psychotherapy Debate. His team works with colleagues in speech signal processing and computer science to develop machine learning-based methods to scale up and improve the specificity of efforts to evaluate patient-provider interactions. He co-founded a technology company, License.io, that is focused on developing new technology for supporting the quality of mental health care. Having said this, we are very happy and grateful to have both Jaime and Zac holding today's webinar, so thank you both very, very much. Finally, I would like to briefly tell you about the webinar tools for sharing your thoughts and questions with Zac and Jaime. You should be able to find on your dashboard on the right side of your screen a hand-raising button. After pressing it, I will open your microphone so that you may speak with Zac and Jaime directly. Alternatively, you may type the question into the questions tab. Here's whether you should also type any technical issues so that I may try to help you. Now, to finally begin our webinar, I will hand you over to Zac and Jaime so that they may start their talk. Zac, Jaime, thank you both very much.
Thanks so much, Juan. First of all, many thanks for organizing this webinar and for the opportunity to connect with colleagues. And secondly, thanks so much to Zac for agreeing to join me on this webinar. It's a pleasure and a privilege.
And just thanks for asking me. This is going to be fun.
So let's make a start. We are both clinicians. We are both researchers, very interested in machine learning, very interested in the future of psychotherapy, and interested in discussing what technology might offer to future developments in our field. Our intention today is to accomplish three things. Firstly, we want to offer some general pointers in relation to what machine learning is, because we recognize that there may be colleagues joining this webinar who perhaps are new to the field of machine learning. So we will first try to cover some basic principles and concepts. Secondly, we will be focusing on a discussion of methodological aspects. And as peer reviewers and scientists that are advancing work in this field, Zac and I will have an opportunity to share some of our thoughts, concerns, and recommendations about quality of research in this field. Thirdly, Zac and I recently had some very productive and very interesting discussions about ethics and what this field and development may imply for the development of psychotherapy and ethical questions that we will be discussing today. Also, we would like to invite you to read the first issue this year, published in January 2021, of Psychotherapy Research, the Society's flagship journal, which has a special section dedicated to machine learning and has published a series of high quality, very impressive contributions and innovative contributions in this field. So part of the purpose of today's webinar is to promote this special issue and encourage you to read those papers to make that easier for those of you who may be new to this field. And Zac and I will try to resolve questions about methodological aspects. Anything else to add, Zac, before we launch in?
I think that was a great introduction. I would say I think this is really exciting, and I think one thing I I would say is that, at least from my perspective, my primary work in this area has been as a well-informed collaborator, and so I work with computer scientists a lot, and have learned a lot of what they how they talk to each other about these things, and a lot of the issues we're talking about today. At the same time, I'm not a computer scientist. We aren't computer scientists, and so I think one of the things, we'll be able to introduce you to some of these topics, but I think one of the things I hope you hear out of this is, one way to get involved in this work is find a computer scientist at your institution and convince them this is an interesting area for them to work around with, instead of Facebook posts. And they might agree with you. It's a fun area for them to play into.
Great. So let's start with definitions. What is machine learning? There are, of course, several perspectives, books, articles that you can read about this. This is a short summary that is fairly accessible. So machine learning is a broad family of data analytic approaches or data mining approaches. This broad set of algorithms are used to discover patterns in data, and they are capable, after being trained to discover these patterns, to recognize those patterns in new samples. So you could draw a parallel to human learning, where we learn certain skills or tasks in a specific setting, let's say a classroom environment, and we are capable then of applying those skills in a different context or a different setting, for example, in the clinic. Machine learning algorithms are made of several moving parts, and the basic building block of a machine learning algorithm is a conventional statistical technique. For example, correlations, regressions, or Bayesian inference. So at the center of a machine learning algorithm is a basic statistical building block. According to these basic statistical building blocks, machine learning algorithms of different types are grouped into families of models. On the slide, you can see one version of a grouping of different types of families of models, such as decision trees, neural networks, Bayesian models, linear models, and others. Textbooks in this area also tend to divide machine learning into two types of learning, supervised and unsupervised learning. My understanding is that supervised machine learning models are specifically designed to solve prediction problems. For example, using patients' initial assessment information and features to predict how they may fare during treatment, what their outcomes may be, whether they may complete therapy or drop out, whether they may relapse after therapy. So supervised machine learning models can help us to solve those kinds of questions or problems related to prediction. Whereas unsupervised machine learning models help us to solve problems related to classification. For example, we could ask questions about whether there are latent classes of different patients in a relevant clinical sample who have shared features and look more like each other. You might think of these as phenotypes, specific latent phenotypes of patients. And finally, the last feature that I will discuss before handing over to Zac is the concept of a pipeline. When you are training one or more of the machine learning models displayed on the screen, you use a process that is referred to as a pipeline. And the pipeline has several moving parts that we will be unpacking and discussing during the rest of this webinar. Zac, do you have any other comments to add about definitions?
Not definitions. I think we were just getting ready to talk before and stopped ourselves because we wanted to make sure we talked about it here. But I think one of the things I think is interesting about this, approaching it from just a psychologist who has standard statistical training that you would get in a psychology PhD program, regression, factor analysis, maybe hierarchical linear modeling, structural equation modeling, those sorts of things, is there's some findings in the area of neuroscience where when people look at these, fancy pictures of the brain that happen in fMRI studies, they stop thinking critically about what's actually happening analytically, and they're not as good as if you just looked at a table that showed the same things, but it wasn't about like what parts of the brain lit up. It was just tables on values. And I think there's a corollary here where we can get overwhelmed with the sort of whiz-bang complexity of all these different sort of new models. And really, at the same time, linear regression is a machine learning model. And so if you know something about how linear regression works, you know something about what machine learning is. And really, a little bit of what we're dealing with is differences in language, differences in culture from people who are trained in a more data science world versus a statistical world, where you can just pick one. Linear models up there at the top. Support vector machine sounds really cool, right? Support vector machine is a logistic regression, essentially. And so I encourage you all to refer to them as support vector machines now in your papers to sound cooler. And so I think, to me, that's one place where I think it can be helpful in terms of getting psychologists to engage more critically when they're reading these papers. That just because you don't have a PhD in computer science doesn't mean you can't reasonably critique at a basic kind of understanding of statistics level what's happening with these models.
Now, that's a great invitation for those of you who may not have delved into the world of machine learning. Zac's advice is that machine learning models are basic statistics in fancy dress. So let that encourage you to look into this. Let's move on. One of the analogies that we like to describe machine learning is this idea of a virtual machine. There are several moving parts that enable you to solve a problem. And usually that is a problem related to prediction or a problem related to classification. Now, machine learning models are a little bit more complicated to train compared to, let's say, ordinary correlation models because they have several moving parts, which means that you as an analyst or a researcher need to make several decisions along the way. And these decisions have important consequences on the accuracy and ultimately the clinical utility of the models that you produce. So on screen, we have a representation of different moving parts that interact with each other, all of which are important and all of which have an effect on the rest of the machine. So in what follows, Zac and I will try to have a general conversation and discussion to share our thoughts and our learning with regards to these various pieces of a virtual machine. Let's start with sample size. As you know, in the field of clinical psychology, psychotherapy, mental health more broadly, we are used to seeing experimental designs that explain their expected hypothesis or an expected relationship between variables. And based on the expected strength of associations, an effect size, for example, it is common to see in research papers that scientists explain what number of cases or data points are necessary in order to answer a research question or test a hypothesis. So we are used to seeing sample size calculations. However, in the emerging literature on machine learning in the field of psychotherapy, it is very rare to see sample size calculations. And my personal opinion is that that's problematic. I'm curious to hear what Zac has to say about it.
Yeah, it's funny. Before the talk, I started just trying to do a little bit of a lit search on PubMed and Google power analysis machine learning. The most recent paper I found was in 2012, and really just it's not a thing people are talking about at some level. And I wonder if some of that is due to the sorts of data sets that people are typically using, where you're engaging with millions of observations. And the other thing is that people don't, this gets a little bit into what you'll talk about later in terms of cross-validation and things like that, is people don't talk about p-values very much. It's not the same sort of idea, but I think there are, when I ask a question to my machine learning colleague, hey, we want to predict whether or not a therapist is empathic in this session, how much data do we need? And their answer is more is better. and so it's been hard to know exactly where to start with that. And there's a number of pieces that can kind of go into it around, well, we're talking about things like reliability, how much signal is in an observation, how much do human raters agree? If you're talking about something like more natural language processing related to capturing something in a psychotherapy session. Base rate matters, right? How frequent is the thing in the population? Whereas if, suicide, for example, there's a paper in the upcoming special issue about suicide where one of the main classification problems is people don't talk about it very much. And so when you're trying to predict it, it's hard to do, and so you need more data. Those are some initial thoughts, Jaime.
I've had a similar experience where, speaking with computer science and statistics colleagues, I've continuously pestered them for references and guidance on how to work out a sample size calculation to train a multivariable prediction model, i.e. a machine learning model of some sort. And for years, I never got a straightforward answer to that question. Until recently, I came across some very useful, very informative publications by the Progress Research Network in the United Kingdom, a group. It's an international group, but many of the leaders of the group are based in the University of Kiel. If you haven't seen their website, it's very, very useful. Progress Research Network. On the slide, you have some references that are very recent from 2019, 2020. In this example, the first paper by Richard Riley and colleagues provides you very specific guidance on how to work out sample size calculations to predict continuous and categorical or binary dependent variables using machine learning models. So very useful references. They demonstrate in some of their work that if you use small samples, for example, less than 100 cases, the prediction models that you train in these small samples do not generalize very well to new samples. And therefore, they may have limited clinical utility if you want to move these into the field of this clinical decision making. So for those of you who are interested in the details of sample size calculation, it might be worthwhile looking into these references, which tell you how to compute sample sizes for training samples. And Archer and colleagues most recently provide guidelines on how to estimate sample size calculations for an external validation sample.
I've already learned something today. So I'm kind of curious to just hear a little more, like, what do they say in terms of how much, because we're thinking about something where you want to design an experiment where we're gonna rate a couple hundred sessions for some variable. Are there guidelines that sort of come out of that, or is it more like algorithms where you put kind of like standard power analysis where you need to put in a number of different things? Yeah.
That's right. So it works very much in a similar way to ordinary sample size calculations. You need a few bits of information. What's your expected effect size? How many predictors are going into your training data set? What is the expected cross-validation shrinkage, meaning the extent to which you expect that the model will suffer, the model's prediction accuracy will suffer in an external sample. That may be informed by previous evidence. So there are some bits of information that you need to plug into a calculator, but effectively it's not that difficult a task, and I believe that some of the collaborators in that group are producing a Shiny R application, so an online calculator. For those of you who use R, this is very accessible. All right, let's move on to the next topic. If we move on to the next piece of the virtual machine, data pre-processing is something that we should also care about. And I'm not sure what you think about this, Zach, but I hardly ever see information when I'm peer reviewing machine learning papers about how researchers prepared their data before they started to implement machine learning. Why should we care about pre-processing?
Well, I'll just take one specific example from our work is, if you're doing research on the words of psychotherapy, that almost never comes to you clean, right? Where it's perfectly formatted and ready for turning it into some sort of quantization framework. And so you have to make tons of decisions about what you're going to do with that data before you ever even fit a model. And so that there's things that are as simple that are pretty common, things like stemming, where you're kind of making words more similar. But one of the big ones that we've ended up spinning around and around on is stop words that folks may never have heard of before, which is about the much of language in human interaction is the kind of and the, it's the really the work of like James Pennebaker, who all the pronoun research that a lot of machine learning natural language processing models simply strip all that away before they do any analysis. And so we've done papers where we've done that, and it's, you know, works fine. But then I think more recently we've actually published some papers showing how some of these words are pretty important for underlying concepts like empathy and kind of how you're communicating with the person more stylistically. And so you can actually miss some signal by removing some of those things, because it's different than a movie review, for example, where you're just maybe interested in the sentiment of the reviewer. And so I think those sorts of issues can have a really big impact on your decisions and what you find in your model.
They have important consequences on everything else. And in my view, data pre-processing decisions are poorly reported. For those of you who are participating, who are active in this field and designing machine learning algorithms and publishing, a suggestion would be to be entirely transparent about at least 4 things. 1, transformation. Are you transforming your variables somehow? For example, if they're skewed, are you transforming them in order to address problems of skewed data? Information about reduction is important. If you have categorical variables with multiple categories, some of which have few respondents, are you making decisions about collapsing those categories into smaller sets of categorical variables? How are you making those decisions? Thirdly, imputation. Are you using imputation of missing data? If yes, which methods? If no, why not? And fourthly, balancing of data. This seems to me especially important in the context where we are seeking to develop models to predict binary variables or events of interest. Take an example of a dropout after therapy. According to meta-analyses in the field, in psychotherapy, roughly 30% of people drop out. That's not the majority, it's a minority, albeit a substantial minority. It is well known that events with a low base rate, 30%, 20%, 10%, are more difficult to predict. And therefore, decisions about how to balance data in the context of small base rates are quite important and have implications for performance accuracy. So, Zac, go ahead. Any other thoughts about this?
I think that's just a huge point. I think there's the results of papers can be almost determined by some decisions that are made there that aren't well reported, or sometimes even if they are reported, they're kind of like this minor little sub piece of the oh yeah, and you know, we selected randomly groups of each class, and then you're like, all of a sudden you're like, wait a second. For example, there's a paper a few years ago in Nature Neuroscience where it was a machine learning case where they were trying to predict cases of schizophrenia in just spoken language, which is, you know, would be a really cool thing if we could do that. Of course, you know, the paper worked really well. It got published in this great journal, but it was equal in both groups, right? So the data set was 50-50 schizophrenia or not, which is not exactly what probably the use case is. Now, maybe you could imagine a use case where we're in a clinic where the base rate of psychotic symptoms is really high, and so we're trying to use this to help us sort things out or something. But if you're using it as a way of screening, it's just that's almost of no utility, because the true base rate's, you know, less than 1% or something like that. And we've had the same issue with, we're interested in things like, do therapists in substance use settings confront people, you know, and do things like shame them or tell them that if you don't change, you're going to die, like stuff like that. And it turns out, thankfully, that's pretty darn rare. People don't say that a lot to their clients, but when they do, we'd like to catch it. It just turns out that because it's so rare, it turns out it's really hard. If we wanted to do a paper where we just created a equivalent sample size in both groups, we could do a pretty good job. So it's not that it's not distinctive. It's just that it's like the needle in the haystack problem.
Very interesting problem. So for those in the audience, what you can tell is that these decisions are very important, often not reported. They have consequences for everything else. So our discussion, I think, raises this as an issue for increased quality in reporting, not least to enable replicability. Okay, let's move on to the next piece. So far we have been talking about preliminary decisions. How large should sample sizes be? How should I calculate a sample size for this specific dependent variable or prediction problem? How should I prepare data? Let's move into the nitty-gritty. So cross-validation. In my understanding, cross-validation is perhaps seen to be one of the defining features of machine learning as a particular perspective on data mining or pattern discovery. For those of you who may not have heard of cross-validation, maybe I can offer a few words in the way of definition, and perhaps Zac can add his thoughts to that. So what is cross-validation? In the simplest terms, cross-validation involves partitioning or splitting a data set into different pieces. These are sometimes called folds, different pieces or folds of a data set. The goal is to enable the algorithm to learn or discover patterns in the data and to test its capability of recognizing those patterns in new folds or new pieces of the data. There are several approaches to cross-validation. For example, split half cross-validation is a method where you split your data set 50-50, 2 equal parts. Use one set to train a prediction model and the other set to test its performance. Another option is to use an imbalanced split where, for example, you may train a model in 70% of the data and test it in 30% of the same data set. Now, in this example, the 30% test split is referred to as a holdout, where you hold one piece out and do not use the samples in that piece to train the model. And this enables you to see what would happen if you use or deploy a trained machine learning model in new samples not used to develop its prediction method. Other methods include leave one out, where a single case is left out of the data set and you develop a prediction model in the rest of the sample. And there are bootstrapping approaches that are also built into some of the machine learning models that are more popular in the field these days. The final thing I'll say about this before handing over to Zac is to make a distinction between external and internal cross-validation. Internal cross-validation refers to a process where you are training a machine learning model using the same data set, and you may be doing iterative loops of analysis within the same data set. Often the goal of doing that is to accomplish something called variable selection. In other words, from a given set of potential predictor features, internal cross-validation helps you to decide which features to keep, which ones seem most useful for prediction or classification purposes. But an associated goal of internal cross-validation is also weight setting. Weight setting refers to the idea that if you have a certain number of variables that are useful to predict an outcome of interest, some of those variables are more important than others. Some of them may have a stronger relationship with the dependent variable, whereas others have a weaker relationship. And weight setting differentially assigns importance to different predictors. So those are some basic concepts in relation to cross-validation. Zac, do you have any other thoughts to add?
Yeah, just to go back to what you said right at the beginning, it really is the key cultural difference between classical statistics that most of us probably have been trained in and the way a lot of this work is done in computer science. And I think it's been the hardest thing for my colleagues to wrap their heads around as I start to talk about this work. And then also as we just started to make inroads to publishing in psychotherapy journals, where we're talking about our work in terms of cross-validation rather than whether there's a correlation p equals p less than 0.05. It's just not the way things get done. When I talk with computer scientists about how we typically fit models in our field, where it's like, so you take all of the data and you fit a regression to it, and then you report that. They think it's cheating. They can't understand how you could possibly get away with doing something like that, and which is interesting, right? And at the same time, they rarely report any sort of statistical significance criteria, and the way they deal with these issues is by holdout samples. And so, what I think the thing that can get difficult, one of the pieces that you talked about, Jaime, was how much of data in the training set versus the test set. And when you don't have, a billion observations, that's not a trivial decision, because the more data you have in the training test, the more you can learn, and presumably the better model you'll have. The problem is then your test set can get so small that when you evaluate it, you're going to get noise just by chance, and so it's harder to know how well you trained the model. And so, ideally, you would have, both a huge training set and a huge test set, but those things are necessarily competing against each other. And then, one other thing that I think we're going to talk about related to hyperparameters is when you start to think about, well, there's all these little things that go into these models, and it can actually get even more where some people have a development set, which is where you do all this pre-tuning and figuring out how you're going to run your models. Then you do a train set, because you don't want to spoil that part of the model, and then you do a test set. So you can break it out even further. And so I think it does, what I've seen a lot in reviewing papers on this is people say, I've got some data, I want to fit a machine learning model, and you may just not have the data to do it. It may be that you've got a couple hundred cases. When you get down to it, well, once I do a test set, maybe I only have 3 or 4 instances of my outcome of interest in the test set, and so it's not going to be possible. So the scale is important.
I think you're alluding to one of the key problems in our field, Zach, which is that the majority of machine learning studies in our field, to my knowledge at least, fit a model in the same sample that they use to test the potential clinical utility of the model. And this is, again, coming back to concepts, internal cross-validation and evaluation in the same data set. And this is problematic because we simply do not know whether these machine learning models trained in this way would perform well in new samples. And it's entirely possible, likely in fact, that studies that are designed in this way are perhaps drawing conclusions that are over-optimistic, perhaps an illusion of overfitting in a training sample. To my knowledge, there are something like 4 or 5, only a handful of studies in the field of psychotherapy that use external cross-validation samples, and even fewer that use completely different contexts. So, for example, our esteemed colleague Marcus Hybers and colleagues in the Netherlands published a fascinating paper in the recent special issue of Psychotherapy Research, where they do a cross-trial prediction. In other words, they use one RCT, or clinical trial data, to develop a prediction model, and they test its potential clinical utility in data from a completely different control trial. Fascinating study, well worth the read. But this is an example of one of the rare efforts that truly test the validity and the clinical utility of a machine learning model in a new sample.
It's my estimation that doesn't happen all that much, even in computer science journals. Traditionally, they'll do a thing where you have a data set, and then you just split it. And you've got some data that your model never sees, but it's not that you're saying, oh, well, I want to build a true emotion detector of positive, negative emotion, and so I'm going to have this data set of people talking to each other on the news, and then I'm going to see if it works in people having conversations about their family at home. Right? That sort of thing is not done very often. I guess the one other thing I would say, Jaime, is just to make a point about why this is important relative to what we might typically do in psychotherapy with p-values and regression predictors and stuff is the scale of predictors you may be using in a machine learning model, not always, but often, is just an order of magnitude larger than what you might do in a typical regression, where you're about, you put in one predictor and you're seeing if that works, then maybe add another one or another one. And like a regression with 4 or 5 predictors would be seen as quite complex. Whereas you could have thousands and thousands of predictors in these models where, potentially every word in the data set is a predictor, whether it's present or not, or some other list of long features. And so to evaluate whether or not you're just not capitalizing on chance when you're not using p-values, you can build a regression model that predicts your own data pretty perfectly. But whether or not it has anything to do with the test set is a whole separate issue. And yeah.
And this, of course, has consequences for implementation. We are, as the field, at the early stages of getting to grips with these new approaches to data analysis, but even at earlier stages in terms of the clinical deployment of decision tools trained through machine learning. So here are some interesting thought experiments for the future. Wouldn't it be amazing if we are able to develop prediction models, for example, to predict the likelihood that a psychotherapy patient may attain full remission of symptoms or presenting problems at the end of treatment as a goal, outcome prediction? Wouldn't it be amazing if we can develop a model that predicts treatment outcomes and that is demonstrably accurate in a sample from not only a different study, but a different service altogether, different geographical location? And not only that, but capable of predicting future cases. For example, a machine learning model trained with data from, let's say, 2015 is able to predict accurately outcomes for patients treated in 2020, 5 years later, in a different geographical location, with different therapists, in a different part of the country or in another country. That is where we need to go as a field, and the good news is there are studies like that in the pipeline from not one, but several research groups. And I'm saying this to encourage people to take interest. This is a very rapidly developing, exciting field, but we have to get the methodology right. Zach, earlier you alluded to a rather complicated topic, a niche topic in machine learning, hyperparameter tuning. Can you talk us through this?
Probably not at some level, but what I will share with you is that what I've come to learn from, Jaime, you may have more detail to say here than me, but I'll tell you what I think about it, what I know, is that when you are getting ready to fit a machine learning model, it's not off the shelf like it might be in even fitting even outside of like SPSS or SAS. You go into the regression program in R, it's just going to run a regression for you. And it's got a number of things that are happening in the background that you're not necessarily aware of, but that the field has decided are kind of the way it works. And so when you get into a variety of machine learning models, this is particularly true for things like neural networks that are kind of all the rage, but it's true for other things like, something that's been around a lot longer, like k-nearest neighbors, which is where you're trying to make predictions about a future data set by all of the different data points that are closest to a predictor data point. And so I'll just, as an example of a hyperparameter, how many nearest neighbors should you consider? 5, 10, 100, right? And so there is, I'll just pick another one. When you're doing a regression, the loss function, sort of whether or not how quickly it learns, is a thing that you can adapt and change. Even some people would consider the size of the training and test set a hyperparameter that you can iterate on and play with. And so there are tons of these things. And from some of the computer scientists I talk with, they write code to iterate over the entire space of these things. And so they have a development set where they might iterate over, all possible values of learning rate, all possible values of train test, separations. And then they come with the, here's the menu of hyperparameters that helps us make the best prediction in the small development set. Then we take those variables and then we move into the training set, and that's when we actually start to learn. And then but we don't mess with the hyperparameters anymore. And so I think it's rarely discussed in papers, and it's a discussion among computer scientists on actually why a lot of machine learning papers, even if you have the same data, it can be difficult to replicate analyses. And so, psychology, we have our own replication crisis happening. That's completely different than this one, but computer science has one they're talking about too, which is, why is it that if I'm using the same model and I have the same data set, that I can't get your result? And a lot of the discussion is actually about this hyperparameter tuning. There's all of these, thousands and thousands of decisions you're making before you finally get to the model you use, and all of that stuff matters.
So I think you've alluded to some of the key discussion points here. It's an obscure and rarely discussed topic in papers, especially in mental health related papers. We could extend that actually to healthcare related papers that use machine learning. But Zac, you're pointing out three really important things for the audience. One, these are decision points. The analyst has to make not one, but several decisions about hyperparameters, which then determine how the machine learning algorithm learns from a training data set. So you can think of these, to extend this virtual machine analogy, you can think of these as the levers and the buttons that you have to set certain levers and press certain buttons before the machine starts working and crunching data. Those are hyperparameters, and they involve making decisions. And Zac also points out that not only do you have to know what these are, make decisions about them, those decisions have consequences, but Zac's example illustrates that there is a manual approach. You can set the levers yourself as an analyst, or there is an automated approach. These days, my understanding, as Zac points out, is that many of the computer scientists that are advancing this field forward are preferring to use automated methods to choose optimal hyperparameters. And there are different expressions in the literature, one of which is a random search or a grid search. Random search being to choose the hyperparameters at random. A grid search is testing every possible combination of hyperparameters. Now, to the audience, this probably sounds rather obscure and niche and full of jargon. So let me give you one example to extend Zac's discussion. One of the approaches to machine learning that I'm finding very interesting to solve clinical prediction problems are generally decision trees, like random forest or XGBoost or Bayesian approaches to decision trees. When you're training decision trees, you have to make decisions about certain things. These are hyperparameters. For example, you need to specify how many decision trees you're going to train. If you're using a random forest model, you might decide to train 10 trees or 100 trees or 1,000 trees. So that's a decision, and it's an arbitrary decision made by the analyst. Another decision is the maximum tree depth. How many levels will the tree have? And what's the relationship between the levels and the number of variables in your data set or potential predictors? Another decision is about the minimal sample size between a parent node and a child node. You can specify to have no less than a certain number of cases in each of the nodes in a decision tree. Now, for those of you who are familiar with decision trees, I hope you can probably visualize what I'm talking about, but for those of you who may be unfamiliar with this, the general take-home messages are there are lots of decisions to make. They have consequences. They can be made manually, which is not advisable, or they could be made automatically. That you could use a grid searching approach, which helps you to optimize hyperparameters in an empirical way or a data-driven way. Now, a caveat to that last point is that this is my opinion, and I'm not sure if Zac has that preference over empirical versus manual approaches.
mean, I'll be honest, this is the part of a lot of my collaboration that feels a little bit the most magical to me, where I'm working with folks who, when they talk through some of the things they're making decisions about, to be honest, I'm not even sure they understand what they are. They've so fully bought into grid search stuff where they have some code that kind of tells them what values to pick, and so they pick them. And so when I talk to some of there's the kind of new generation of computer scientists, and then there's like the old school ones who maybe have a bit more classical statistical training, who think this is just scary and abhorrent, and that we're doing a lot of the kind of performance and power of the new neural network models that are coming out are making people implement things that they don't really understand. And so I think my guess is that there may be a trend towards people having to report these a bit more in papers and to be thinking more about the impacts they might have. But it's not something I have a great understanding of, other than I can think of corollaries in my own work where something like you were talking about, where there at times can feel like it's a bit of a tension between, is this fully a model parameter or a hyperparameter, where if you're fitting a topic model, for example, a topic model is like other latent class models. You have to pick the number of topics, right? So does this topic model in a document, I'm going to do this big document discovery of how many groupings of topics are in these documents, and the model doesn't know how many to find. And so you have to tell it, right? And so what I've seen, kind of, I don't know if this is scary or makes it more approachable, you just kind of play around with it and like see, okay, well, when we have 5 topics, it seems like we're probably missing a lot of richness. But if we put 200 in, it looks like there's some arbitrary parsing where there's topics that are really quite similar to each other, where the distinctions are meaningful. So let's try 75. And so I've seen that happen. But then there's also the kind of more automated approach where you sort of iterate all over those number of topics and try and use some metrics to help you understand which are the best ones.
I think the key point that you raise, Zach, is full reporting, so that the field can evaluate these and we can learn from each other and replicate each other's work, and so that together we can understand more about hyperparameter tuning. All right, let's move on to the next topic, which is on-site.
Jaime, before we move on, I actually have a personal question for you. It's more on the philosophical side of things, maybe. This is sort of feels like a sci-fi movie where the researcher takes decisions in machine learning, but also there's an automated method where even the machine starts making these decisions. So where do you think the researcher will stand in the future, the psychological researcher in regards with machine learning? Are we going in a direction where it will just be designing the machine and letting it ask its own questions, for example, in the long run? Or where are your thoughts on this matter?
Zach, I defer to you on this matter. We were having a fascinating conversation about this a few weeks ago.
It's a good question. You know, one thing I might, a particular example that I might go with on that is just to go with topic models again, just like factor analysis. So you can have a model discover these factors, these topics, but the researcher has to name them still, right? And so there's still a human being who like looks at this data and says, oh, well, these items are all about hopelessness, or all of these words in this topic are about family problems, right? And so then you label the topic family problems. There are now topic model approaches that will label the topics for you, right? So they will do the topic discovery, and then they'll look over the content of the topics, and they'll do a discovery process where they actually automatically label what they think the topic should be called. And so I think there is movement in that direction, probably not as far as maybe you're thinking it, but that where a lot of these decisions, you know, you will start to come across, I would assume at some point, SPSS will have a neural network package, as scary as that might sound. And, you know, all of us will be able to implement those things. I think Watson, IBM's initial take on AI was an initial trial at that. And I think what they're going to be doing is start to move aspects of Watson into SPSS, which IBM owns. But the thing I would say is, so a lot of these things will get automated in the background because that's like what's happening with linear regression now, right? You don't make all these decisions about linear regression. You just fit the model, and there's things you play with, but for the most part, most researchers aren't thinking hard about the learning rate in your linear model that you're predicting. I'm a little skeptical that we're going to get to the point where the machine's telling us what questions we should be asking. I don't know, maybe, but I think the question is, the role of scientists will still be, and I think this is really the role that I feel like psychologists play when they're working on large collaborative teams with computer scientists and other technical experts, is they have tools, they don't have problems, right? We are the ones with the problems that are interesting and important at some level, and it's our job to know enough about the methodological approach that we can understand what it might be able to do, what could be interesting, and then to really think through with our colleagues about what sort of problems can this address that are persistent and hard in our field. So I guess that's what I think about it.
Interesting thoughts. So we have tools, not problems. In psychotherapy, we have lots of problems that we need to solve: dropout, poor outcomes, deterioration, relapse. And the tools of machine learning, I think, can help us to give my perspective on the colleague's question. My view is that these tools, the machine learning models, lie on a continuum from highly interpretable models to black box models. And there is a debate in the field about whether black box models are ultimately possible to implement in healthcare environments. So, for example, as Zach was explaining earlier, there are machine learning approaches that are very, very similar to conventional regression. For example, regularized regression models like ElasticNet or Lasso are very, very close to conventional regression. They have a few additional features. And the advantage of those, in my view, is that they are highly interpretable. You know how the model's training, how it's learning from data. You know what the predictors are that are being selected. You know which ones are more important than others, and you can explain that to a therapist. So I can say to colleagues in my clinic, we've investigated data from this service. We know that patients with certain personality traits tend to have poorer treatment outcomes, and these are those personality traits. We also know that patients with comorbid long-term health problems like diabetes or coronary heart disease tend to have poorer treatment outcomes compared to those who don't. So it's highly interpretable. I can explain this in a way that's clinically intuitive. On the other side of the spectrum, you have black box models. And I think neural networks are, I guess, the classic example of a black box model. We have a conceptual idea of what's happening, but we really don't know how the model is learning and how it's making decisions. So this all sounds a little bit like science fiction, I think was the comment. Yes and no. It does sound like science fiction if you train highly complex, uninterpretable models and you try to convince psychotherapists to make decisions based on such models. But it doesn't look like science fiction if it's highly interpretable. So I guess there's a continuum, and perhaps as a field we need to learn about first how to train reliable machine learning models that have good predictions that are clinically useful. And next, our challenge is how can we ensure that this doesn't sound so much like science fiction to our peers in clinics?
I want to underline that point. Like if folks took away two things from the talk today, I think one of them would be this idea of cross-validation and how essential it is. The second one to me would be this tension between explainability versus black box, which I think is it's like a huge thing in computer science. And they're coming to the tension of like, oh, we can create these amazing models that predict all this stuff, but nobody has idea. We don't have any idea how they work. And I think when you bring those models into our literature, I mean, I can remember having early conversations with my colleagues where we're like giving them all this data where we've rated empathy and have all this rich, conversational data that's feeding into these models that's learning how to predict empathy in a psychotherapy conversation. And built a really good prediction model. It works really well. And I go to the guy who built the model. I was like, okay, well, this is really cool. Like, what does it mean about empathy? And he's like, what do you mean? What does it mean? It means if you give me some data, I can predict it. and so functionally, it means we've learned nothing about empathy. We've just learned that if you give me a bunch of human ratings of some interactional data, I can predict a score that a human being would generally give of that same interaction. That's very different than I think a lot of the typical work we're doing scientifically. We really want to understand what is empathy, and we want to build models that help us understand that. So the goals are really, really different.
So this discussion point, I think, has a relevance to this particular concept you have on screen, ensembles. What are ensembles? In the way of a brief explanation, perhaps we don't have to dwell too much on this specific subject, but there is a trend now in machine learning which is examining whether a combination of machine learning approaches or models may give you better predictions or classifications. So the idea being that you train a machine learning model with one flavor of statistics, let's put it that way, let's say decision trees, and you use the same data set to train a different machine learning model with a different approach, let's say support vector machine, and you combine the predictions from different algorithms. Now you can do this with 2 models or 10 models or 1,000 models. And there are people who are doing interesting simulation studies and now using clinical data to assess whether ensembles can help us to make better predictions or classifications. But this brings us back to the problem, the tension between interpretability and, let's say, complexity. Will ensembles make a difference? Maybe they will help us to predict things ever so slightly better, but perhaps they're more difficult to explain to psychotherapists in clinical practice. Zach, do you have any other thoughts about ensembles before we move on?
Yeah, not much. I mean, I wonder if it could be, I'm on kind of unfirm ground here. The folks that I've worked with and most of the machine learning papers I've contributed to that have gone into machine learning journals, where the standard idea is we want to develop the new cool model that beats all the other models. And so the kind of typical result is we've got these baseline simple models, and can our new fangled machine beat the other ones? And so I haven't really been a part of a lot of collaborations that have been about ensembling. It's been more about new tweaks on neural models or playing around with different parts of it. So I just have less to say. I see it happening, and I know there's packages for it in R and things like that, but I'm not as familiar.
So it's an open question for the field. Will ensembles help us to make better predictions? Who knows? And will they be interpretable? That's an ongoing challenge. All right, let's move on to the last piece before we open up a wider discussion. I think we're doing well for time. We've got the best part of half an hour, I believe. So evaluation metrics. The whole point of developing machine learning models is to solve problems. And those problems, generally speaking, are problems of prediction or problems of classification. How do you know if your machine learning model is good at solving these kinds of problems? So the convention in the field is that you train a machine learning model and you want to develop an algorithm that maximizes prediction accuracy and minimizes prediction error. And we use different metrics to evaluate how well a prediction model is performing, ideally in an external cross-validation or validation sample. Now, there are different types of statistics that you could use for evaluation purposes. There is an emerging consensus in the field. For example, this paper by Handelman and colleagues, it's fairly recent, is a useful reference because it discusses different types of metrics for the evaluation of models, depending on whether you are predicting a continuous, categorical, or binary outcome. Zach, do you have a view about evaluation metrics or any preferences?
Just a couple of points, where I think actually psychologists have some decent training to be thinking through these issues where, typical things around, sensitivity and specificity, although it would be labeled often by different names in machine learning, precision and recall. You'll see ROC curves a lot and area under the curve in these types of things. And so, but I guess the same rules apply where, my own lab right now, we're working on trying to detect whether or not a therapist is doing suicide risk assessment. And we've got 10,000 statements in a crisis text line data set, and risk assessment happens maybe 50 times. And so your accuracy, if the model just said it never happens ever, is 99%.
Yeah. That's
right?
a classic low base rate problem.
And so that's, it's the same thing with classical test theory and all this other stuff we would have had in probably our class we would have taken early on in graduate school. And so like the same thing applies. And so you can't just look at accuracy, you've got to look at other things. And there are, typical metrics that you're starting to see more, like F1, which wasn't something I was aware of until I started working with machine learning colleagues, is it's essentially a weighted average between precision and recall. Where you're kind of getting one metric that's telling you how you're doing on both, and so it's got some similarities with ROC curves. But even those, there's no one perfect metric. Depending on base rate, depending on how the model's making errors, you can fool yourself, and so can reviewers. And so it really makes sense to look at a lot of different metrics and then try and get a gestalt of what you're seeing.
Great point, great point. And my reading of the literature is that this is where, let's say, the good practice guidelines are moving towards. Don't rely on a single metric, for example, an R-square in your holdout or test sample. Use a variety of metrics to get a well-rounded perspective about prediction accuracy, first one, prediction error, there are different metrics for accuracy and error, and calibration, how well your model is performing in different scenarios. Could it be that your model is, following Zach's example of an event with a very, very low base rate, a model that says nobody is classed into this group would perform very well if we think of it from the point of view of specificity, but it would be performing very poorly if we think of it from the point of view of sensitivity. So you want to get a sense of a well-rounded set of metrics, and the guidelines in the field encourage us to pay attention to accuracy, error, and calibration. For those of you who are interested in further details, again, I would like to remind you and invite you to look at the special issue of Machine Learning in Psychotherapy Research. The introduction to that special issue has useful references for evaluation metrics, and there is a very, very nice a scoping review of machine learning in the field of psychotherapy. The discussion section of that very, very good paper also thoroughly considers the relevance of evaluation metrics. All right, Zach, let's move on to some of the more perhaps contentious but also fun topics to discuss. We had a very productive discussion about perhaps what we see as the future of psychotherapy and how the advent of machine learning and artificial intelligence technologies might change our field and our practice in the future. Would you like to start by sharing some of your thoughts on ethical considerations?
Yeah, I mean, I guess, if you went 20 years ago and you were running a clinical trial with, 500 participants, so like a huge clinical trial for psychotherapy, right? And you did the math, it's a CBT trial, and everybody gets 20 sessions, and you're recording them all you're going to check fidelity on, one session a month per therapist or something like that. Most of that data, nothing ever happens to it. It sits in a filing cabinet maybe at the time, but now it would sit on a hard drive somewhere, a server. And no one thought like, oh, well, are these 20,000 conversations that happened in this study valuable at some level? Could we learn something from it? Because we didn't have the technology to do anything with it. And I think the thing that shifted in the field is that now we do. We have technologies that can take really, really large and sensitive data from our trials and make it useful, right? So when it used to be, when NIH makes you have like in at least the US side, you have a data sharing agreement through an NIH-funded clinical trial, they were telling you, oh, we should put the, the symptom outcome data and the, kind of the main outcome data for the study online in clinicaltrials.gov so other people can work with it. They weren't talking about you putting the recordings for the entire study online so people could work with it. Because at one level, right, that's crazy, that's too sensitive. And another level, well, what would we do with it anyway? And so I think once that calculus changes, it makes a lot of conversations a lot more tricky. And the companies that are springing up to do this sort of stuff, the Talkspace, BetterHelp, Lyra, you name it, Ginger, IESO in the UK. These are really cool companies really doing really cool things, but they partly think of their value as we're capturing all of this conversational data. We're going to learn about psychotherapy, and then we're going to, either help improve our therapists or build their therapists that aren't even humans, or who knows what they're going to do exactly. But I think it's a real shift. And so I think just that whole idea makes us think differently about some of the research we do and what it means.
And I'm pretty convinced that this will lead to discoveries in terms of how therapy works and shifts in our theory. I've tended to think that perhaps in the field of psychotherapy, at least relative to other domains of science, we tend to be very theory-driven and theory-heavy. Perhaps sometimes to the extent where it serves as a sort of tunnel vision, where when you're listening to recordings of your therapy sessions or those of your trainees or supervisees, you tend to listen out for things and selectively attend to things based on a theoretical filter. And I'm not sure after decades of therapy process research that we have learned a great deal and that we will continue to learn taking that theoretical perspective, which is what excites me about machine learning. There is now the possibility, and it's within grasp, to train algorithms to discover patterns in audio data, in visual data, and in text data that are atheoretical, that don't have the theoretical tunnel vision, and that could potentially help us to discover new insights about how therapists interact with their patients. That's one of the aspects that really excites me, the potential to really shift insight and theory through a purely data-driven approach. Now, I recognize that not everyone in the field of psychotherapy shares that perspective, that, let's say, data-driven perspective, but I'm curious to think about your opinion about this, Zac. The theory versus this, let's say, pattern discovery tension.
Yeah, I mean, I have the same concern. I mean, and excitement, and so you could take just a different example, radiology, right, where there have been, I feel like probably even further along than us. This is looking at a chest scan for nodules, maybe for some sort of cancer. This is a highly skilled, highly boring, potentially, task where you're looking at these repeated scans, and radiologists are paid lots of money to capture them. And there's a variety of papers showing that machine learning models can do this more accurately than humans can. And now it seems like the questions are more about implementation and then the ways in which all these models can get tricked, right? And so these models are statistical models, they're not human, and so they don't have, there's been some examples where you can put in really wild things into these chest scans and the machines won't look for them and don't recognize them because they haven't been trained to do it, because it's a very specific sort of intelligence, right? And also the machine, we like this particularly in psychotherapy. If you ask the doctor, you ask the therapist, why did you do that? They can give you an answer. Now, whether the answer is accurate, whether or not the therapist has great insight into why they did X or Y, who knows, but they can certainly give you therapists are really great at explaining their behavior. We learned to do it in graduate school. And the machine cannot, for the most part, at this point at least. It doesn't, you can't ask it, why was that rating a 4 or a 5? Or why did you say this case was this or that? Especially the most effective models, the best black box models, don't give you answers. They just, on why things happen. And that can be even more concerning with, biases in algorithms where, there's lots of evidence that these machines work really well on the data sets they're trained on, which is often majority groups, right? And so how might they perform in really high stakes scenarios with people who weren't well represented in that data? Or on, you could take it a couple different ways. Patients of specific minority groups, underrepresented groups, or even therapists who are being evaluated from different minority groups who might not be evaluated appropriately. And so when you start thinking about these things at scale, it can get pretty scary. But I also think some of it is already happening. And so I think it's important for us in the field to start talking and thinking about these things, because I think they're going to start happening to us if we don't.
So two interesting points there, Zach, I'd like to pick up on and maybe expand on. Machines do not have, let's say, meta-awareness of what they're doing. That's an interesting point, and that's why they're machines. The other point is that machines also have blind spots and biases. Although the first of those problems, if we see it as a problem or limitation, is perhaps not so concerning and maybe even reassuring, because the moment that our machine learning models start to think autonomously and think philosophically, that I might start to worry then. But the other problem more seriously is that algorithms can have built-in biases and blind spots. What do you think can be done about it?
So one of the first papers we ended up writing, one of my colleagues who's in design that we've been writing with for a while, one of his primary areas is on designing machine learning based systems that interact with users. And one of our first papers, the title of it was "It's Hard to Argue with a Computer." And we basically found, I was really worried that if you present therapists with any feedback from a machine, they're just going to be like, oh, this is nonsense. This machine can't tell me anything about my therapy. And you certainly have those people. And at some level, they're right. This machine can't tell you everything about your therapy. It doesn't understand that. It just gives you some potential information. But there's actually another group that's like, oh, I guess that's what the computer said. It must be right. And that group to me is equally, if not more scary, because it's also not true. All the machine is doing is replicating human judgment at some level, at least the algorithms we're using. And so they need to be challenged. And so we have another paper that's a little bit more to answer your question. The title is called Designing Contestability, where you actually try and build into the system the idea that this is not truth. This is one guess. It's a tested guess. It's a scientific guess with data behind it that we've evaluated. It might be better than your random supervisor who's just saying what they think, which is what we have now, but it's still just a guess. And we need to design these systems in a way that invite people to look under the hood and think about what they're getting rather than just to present it as this is what it is. And I would assume we'll end up seeing examples of kind of across the continuum. And we're starting to see that with, systems are trying to implement algorithms that predict whether people are at risk from suicide from medical records. And that, has a huge amount of positive potential. And it also could be problematic, right? Where if it's got a bunch of false positives or, who knows?
So our next challenge as we move towards implementation sounds like it's the continual learning or training of these algorithms to overcome biases and to be less susceptible to error. All right, I'm conscious of time, and it's probably a good idea for us to open up the dialogue to the wider audience. We're doing well for time, actually, nearly 20 minutes left, but that hopefully gives us enough time to answer any questions or have a wide discussion. But before we do that, Zach, we cannot move forward without asking you to talk about the Uber phenomenon.
Yeah, I mean, I think it's just one, folks may be aware that Talkspace is going public, right? And there's going to be other versions. I think, as far as I know, this is the first large-scale psychotherapy company that is going to be kind of that well known. They're, Talkspace, one of the first companies to market psychotherapy broadly beyond, the little videos that we've seen randomly. And so I think it's interesting to see the way some of these companies are thinking about how therapists are engaging in those platforms and whether or not that's a trend, right? Where we are really well-trained people who access our patients through an app that an external party controls. And I think even a year ago, most of us would have said, oh yeah, that's interesting, but it's kind of super niche. And it still is kind of niche, but that was before psychotherapy went completely online almost. And I think there's a lot of questions about to what extent does it go back in person. I think it will, but to what extent does the kind of some substantial minority of it remain online? Because there are some clear advantages to patients in terms of accessibility and convenience and accessibility of therapists. But there's some, clear costs, obviously, to therapists around autonomy, how our profession is viewed, how do we develop our own kind of practices. I think we really have to think hard about what's happening here. And there's two sides to it. One, at least within the US, I think the way the mental health system is structured in terms of psychotherapy has not served patients well. Most people cannot access psychotherapy easily. And it's hard to get a therapist, wait times are long. And these solutions might be really helpful to people, even if they cost us some autonomy and some accessibility, and at the same time could be really, really threatening to the status quo in the field and harm patients in ways we haven't thought about yet. And so I think it's really tricky that we're now starting to think through good chunks of research in our field being sponsored by private companies, which is something that pharmaceuticals have been dealing with for decades and have gone through their own processes of dealing with that. But it's been hard to make psychotherapy into a product, so nobody's really ever done it like that for the most part. And I think that's going to start to happen. So I think it's in time. Yeah.
It's a brave new world. These days, more psychotherapists have computers with cameras than divans. Let's move on. Juan, over to you. We have shared our thoughts about the topics we are interested in, and we hope that it was of interest to the wider audience, but let's connect with other folks now.
Perfect, Jaime. Zac, here we have a question from Sergio Davila Santana from Puerto Rico. He's asking if machine learning is being used in psychodynamic or psychoanalytic models.
Jaime, you might take that one. I'm not sure is my answer.
So there are some applications that I'm aware of, but they are very specific. For example, Wolfgang Lutz's group in Germany recently published a paper which is featured in the special issue of Psychotherapy Research, where they develop a way to decide whether patients that are presenting for psychotherapy are more likely to benefit from psychoanalytic psychotherapy or from a cognitive behavioral therapy approach. So how do you accomplish that? You observe the features of patients who seem to respond well in treatment A and treatment B, and you can design algorithms that are capable of recognizing these patterns and of automating those decisions. And you can think of these as advanced treatment selection algorithms. So that's one example that I'm aware of. Zac, do you know of other examples that involve psychoanalytic approaches?
Well, I know, at Bar-Ilan, Donna Atzel-Slonim and some of her colleagues there are working on this sort of stuff and are coming out with papers. And so I think I guess I would step back a little bit and say, can a human being reliably rate the concept you're interested in, whatever it is? And so this is often the question we get asked when we say, I want to try and build some machine learning model of a thing. And so when you think about transference or relational patterns or those sorts of things, the question is, if you want to train a machine to capture it, or the question first is, can we reliably capture it with humans? And I think those things, the more difficult and conceptual the concepts get, the harder that is to do, right? And so it's not surprising that our machine learning work started in motivational interviewing, where we're trying to capture things like open and closed questions and reflections and concepts that are pretty directly observable and easy, and you can get reliable ratings. But if we move into those, I think it'd be a really interesting process of development to see how you might move into more complicated processes. But my guess is if you can get humans to agree, yeah, that's it, you can get machines to capture it.
Great, thank you very much. We have another question from Lorenzo Antici. He's asking if could machine learning help to identify attractors and the change of these attractors in dynamic systems?
Very interesting question. So I have an invitation to read some of the work that is happening in the field of ideographic measurement, where measurements are collected at several time points in the day, for example, through an app that encourages you to complete some simple questionnaires to rate your emotions several times a day, intensively, using EMA technology over several weeks. It's possible to investigate patterns of fluctuations and relationships between different types of emotions or types of symptoms over time. So you could think of these time series, which of course are some of them are highly autoregressive. So a measurement at one time point is likely to be related to a measurement at the preceding time point. So these are complex measurement systems. Machine learning appears to be especially useful to parse and make sense of intensive data such as this. So there's very interesting work put forward by Aaron Fisher, for example, investigating time series measurements and using machine learning analyses to make sense of these data. Zach, do you have other examples or ideas?
I mean, I guess I would, one way to, this isn't a true scheme, but I think it's helpful here. You could think of machine learning models as one level like predicting features, and then it's sometimes predicting outcomes, right? And so there's a fun paper by the IESO group where they use a machine learning model to predict features, which were, is the therapist using one of some large set of CBT skills? And then I think there's a list of like 20 or something. It might have been more than that. And then they use those features, like whether or not the therapist used those skills, as predictors in a model, right? And so the actual predictors were machine learning derived. But then they just built a standard regression model and predicted whether or not the patient got better. And so I think some of what you're asking is same here, right? So we've done, I really shouldn't talk about dynamic systems very long, but we've done a little bit of dynamic systems work where we're using like emotions, patient and therapist emotion as serving in those different roles. And we've done machine learning models showing you can do a pretty good job predicting positive and negative emotion from transcripts. And so is there any reason you couldn't do that and then use those variables, those outputs of those models as inputs in a dynamic systems model? I don't see why not. But I'm sure there's other more complicated ways of how machine learning interfaces with dynamic systems directly, and I don't know what that is.
For our next question, we have a raised hand. James, go ahead.
Hey, thanks for the talk. I wanted to ask how Listen.io and kind of other AI systems or machine learning systems are already being used clinically. My understanding is I think that their applications for supervision, and I was wondering if there's ever a scenario in which one of these machine learning systems might actually be used live in session. I'm thinking of a therapist with an iPad understanding, oh shoot, I just asked a close-ended question, or hey, I'm being super unempathetic right now, or my eye movements are all over the place. There's a notification like that. What's the feasibility of like the spectrum of kind of using machine learning in session?
Yeah, I think so. The latter part of that question, some of it is it's more of a learning sciences and a user interface problem than a machine learning problem. And so, could you use software like Listen live in a session if we optimized it to where it was fast enough? You could. Would that be useful? I don't know. Like, it could be just really irritating, right? And distracting to the therapist process and taking you out of the moment with your client. Where I think, though, the use of that sort of technology is really promising and interesting. And I just know they do it. I haven't actually seen the platform myself, but a company like IESO I know is using those sorts of algorithms live, but they have, you know, the therapy is completely mediated technologically, right? And so you've got a text-based platform, and you can type something, and then the algorithm can make suggestions about things you might try next, and that doesn't disrupt the flow of the interaction. And so I think it's fair to, one question is, now that psychotherapy is happening like this, you know, what if there was some sort of analytics in the bar next to my head that was telling me, Zach, you're talking too much, shut up, right? Or the client seems really distressed and you're not attending to it. Or I mean, you could think of a number of different things, the sort of equivalent of the bug in the ear. But I don't know of any implementations of that in the telehealth context. I just can't imagine they're not coming, because the technology lends itself to it so easily.
I had very similar thoughts to Zach. I really like your metaphor of the bug in the ear, Zach. That's a really nice way to think about the future of these technologies. You have some form of platform that is giving you suggestions that are based on observed cases in the past that are where there are good reasons to implement such interventions because it's been seen to be effective in similar cases. Now, there's the bug in the ear as a metaphor that we could use to imagine what the future of psychotherapy could look like. And another metaphor that I really like is the rear view or the wing mirror in a car. What's the purpose of a wing mirror in a car? Well, its purpose is to enable you to see your blind spot, to enable you to see things that you couldn't possibly see when you're focusing on the road, on your target, on the destination. Sometimes it's necessary for you to look sideways into your blind spots to watch out for difficulties or problems or potential disruptions to the therapy process. I also like that metaphor, and that perhaps is more akin to what's happening already and has been happening in the field of feedback-informed treatment. Feedback-informed treatment models are automated, computerized systems that are like that wing mirror. They alert us to things that we may not be able to see immediately. So if we imagine the future of AI-assisted psychotherapy, perhaps it will be a computerized version of the bug in the ear and the wing mirror in a car.
Yeah, just one little example of this. So there's been some ongoing research at this that I've seen published out of Microsoft Research, where they've been look at like sort of live interactive systems that give you live feedback. And there's been some stuff they've tried with doctors' offices where they have like a big screen behind the patient and it's sort of giving you analytics in real time. I haven't seen any things beyond that in the paper, but one of the things they did, and it got written up in the Washington Post, is they built a little tool where they just had a watch that would listen to the conversations you were having with your partner. And, you know, Amazon's eventually built this thing that's out now, but they were testing it where it would just tell you, it would give you some information about how your partner that you selected might be feeling. And so the author of the work was having a fight with her partner in a car, and the partner was fighting back. And then at some point, like 5 minutes later, she got a text message that said, hey, your partner might be upset. And so, you know, how useful is that? I don't know,
5
but
minutes too late.
It's pretty funny. And you could imagine maybe eventual things that could be useful.
Great example. So I believe we have 2 minutes left. Juan, over to you.
We don't have any more questions. Oh, yes, we do. We have a raised hand from Gustavo. Whenever you want, Gustavo, you can turn on your microphone. Okay, there it is.
Hi. Listening?
Yes.
Hi, do you listen? Yes. I want to ask if there is some application of Internet of Things. I mean, some sensors or in the body, like the heart rate, or some sensors to implement an input in the artificial intelligence. there are some investigation or research in this area or with this technology that is known as Internet of Things.
So I believe this is a question about biometrics and the collection of biometrics, such as, let's say, cardiovascular data or sleep-related data. I am out of my depth with this one, Zach. Do you have any ideas? I haven't yet collected such data.
Mostly me too. I think some of it has been because we've been interested in data we can get fairly unobtrusively without asking, it's enough to get therapists to record things versus asking them to, instrument their client or something like that. And so even if it was, a watch, I think just adding that, is another thing. But I'm aware of stuff like that happening in research. Again, I think Donna Atzel-Sloanim's group at Barlan, I think, is doing this sort of either captioning skin conductance and other things live, along with other sorts of types of measures. And I think there will be interesting stuff that comes out of that. For the foreseeable future, I think it's mostly going to be research-based, where people are trying to ask questions about basic interactions. But I haven't seen applications clinically, beyond like typical biofeedback stuff that's been around forever. But it'd be interesting to see it if anybody knows about it. I'd be curious.
Right, thanks.
So I believe that we are now out of time, Juan. So from my part, I'd like to say I really hope that we haven't put people off. Instead, I hope we have pulled people in to find out more. And please remember to check out that new special issue of Psychotherapy Research.
Definitely. Well, I want to read to you one last comment that we have in the Q&A box. Kim DeYoung is saying, "Thank you for this wonderful overview and making machine learning less scary." So definitely, it was great. We have a lot of comments saying how great the talk was, and personally, I want to thank you both for such a fascinating, great, and very clear overview on what is machine learning and some of the methodological and ethical considerations in the field of psychotherapy. So thank you so much to both of you, and also thank you very much to all of our audience for sharing with us this event and their participation and their attention. This webinar is being recorded and it will be uploaded to the Society for Psychotherapy Research Vimeo channel. And I want to invite everyone to look us up on the official webpage and our social media so that you can access this webinar and many other recordings, and so you don't miss out on any of our next events. So once again, thank you all. Thank you, Jaime. Thank you, Zach, and see you next time.
Thanks, everybody.